Welcome everyone to Smart Vision Lights Machine Vision Lighting Basics, Module 3, Color Basics. We're going to begin today by looking at what is color. This can actually be a pretty complex topic, but we'll keep it simple. In terms of interaction with objects, we've talked about in previous presentations how light is either reflected, absorbed, refracted, or transmitted through objects. When we're dealing with the color of an object, your eyes see the color that is not absorbed. So grass is green because the grass absorbs blue and red, but reflects the green for your eyes to see. Sky is blue because it absorbs red and green and transmits blue through the atmosphere. What you or a camera sees is the reflected light that is rejected or left over from the object that is not being absorbed. So when we deal with cameras and colors, today we're going to deal in simplest terms with single chip color cameras, which usually have a Bayer filter. Most commonly today might have complementary color or other filters if they're older. In a Bayer filter, half the pixels are green, 1/4 are blue and red. The true resolution is then reduced compared to a monochrome. Missing pixels information is then interpolated. A blue pixel gets its green and red values from its neighboring pixels. A red pixel similarly gets its blue and green values from the neighboring pixels, and so forth. The color levels are adjusted by the white balance in the camera to be sure the color is accurate and white. So the pros and cons of color imaging here. Color imaging, the pros are you get more differentiation. In certain applications, color is a discriminator and may provide additional information. Color matches human vision. In today's day and age, most people like to see the color images just because it matches, even if it's not relevant to the machine vision application. And they tend to go with color because it just looks better. But there are actually some cons to color imaging. You get less sensitivity due to the color filters in the camera. And if you look at the two graphs I have at the bottom, this is from a Kodak 4 megapixel KAI 4020 imager. These are real quantum efficiencies and absolute values. So you notice the color one, the peak sensitivity is right around the blue range. It's in between the blue and green like the monochrome, but the blue channel is the highest, but it only has about 45% quantum efficiency. Whereas if you look on the right, you will see the peak quantum efficiency is somewhere between blue and green and actually is closer to 57 or 58%. Similarly, you can see that the red peak quantum efficiency is only about 30% just in front of 600 nanometers, but you can see it's probably 40% or better on the monochrome camera. So the filters are absorbing some of, are using up some of our sensitivity due to the fact they are not perfect transmitters. This has an effect that lowers the dynamic range. The dynamic range is a function of the signal to noise ratio. And obviously, if we start with more signal at the imager source, we have more dynamic range. As we mentioned, when you're dealing with single chip cameras, the spatial resolution is reduced for a given equal imager resolution compared to monochrome. So if I use a 4 monochrome color camera and a 4 megapixel monochrome camera, then the color camera has less spatial resolution than the equivalent monochrome camera. And more than anything, color may be a discriminator, but it also means that there's more data. Each pixel in 8-bit monochrome resolution would be 24 bits in color because each pixel has a 24-bit value, which is made up of an 8-bit red, 8-bit green, and 8-bit blue sample. So there's more data to look at, but also more data to process and heavier burdens in processing the image in your machine vision system. Monochrome imaging then and cameras offer almost the opposite. They have the best sensitivity, the highest spatial resolution for any given imager resolution, better dynamic range, and produce less data based on an 8 or a 10-bit sample and not 24 or 30-bit color per pixel. The cons, though, are you get less differentiation and it doesn't match human vision. And again, I've mentioned this because I see this a lot. A lot of applications may not require color, but the operators and people looking at the system are just more comfortable if it matches their human vision. So then you might ask, why use color lighting at all or color in machine vision? If monochrome has many advantages, why would we suggest using a color camera or color lighting and filters with a monochrome camera, as we're talking about in later slides here? The visual representation of human vision is one reason to use color, and color can provide additional information for discrimination, confirmation, enhancement, or elimination of features. So these are important in machine vision, and you may want to use color if you need additional information in one of those areas, and only true color if you need to match human vision or make it nice. But even though we may want to use color and color features, do I have to use a color camera to take advantage of the benefits of color imaging? And the answer to this is no. Many color basic principles can be applied using monochrome cameras and colored lighting or filters in conjunction with them to get to the result we need for the machine vision application. So, color and monochrome cameras typically can need different lighting. Color applications can have different combinations of camera and color of the lights to enhance what you want to see. So there are three basic areas we're going to talk about today. Color discrimination, which is most commonly a white light in a color camera. This means we want a full color image, and we want to either identify specific colors very accurately, or we want the image itself to be color through all aspects of the image. Color confirmation means that we can use a colored light, and we might use a color camera, but we might also use a monochrome camera to get confirmation. And this means we're going to separate a color from others or brighten and enhance the color. Color elimination then is just the opposite. We're going to use colored light, and we still may use a color or a monochrome camera, but we're going to eliminate or decrease the contrast of certain colors to get to a certain result we need in an application. So the first category of color discrimination basically deals with what color is it. And in this case, we have a bunch of M&Ms there, and you want to see bright colors on all the M&Ms, and you might need to see them to see they're okay. Again, white light, color cameras, observe the scientific method rules that we've taught in the first presentation to get good signal to noise ratio and a solid image. But otherwise, you're going to use the light structure, placement, and good imaging practices that we taught you in other trainings to build a solid image result. Color imaging in this aspect, when we need full color for color discrimination, is really no different than monochrome, and all the same good practices apply. The only difference is you're likely going to be using a color camera and white light. And then once you have a color image, if you are doing machine vision with it, besides the human eye seeing the color image, there are different color tools in machine vision software to deal with color, separate them, and make a choice compared to simpler monochrome tools. This then, in this sense, then color imaging is similar to monochrome imaging, and again, everything we've taught you applies. This is not what we're going to build on today so much, because this is pretty straightforward to good imaging practices. What we are going to talk about today are the basics of color mixing, and there are two basic rules here. Rule number one says the same color brightens. So if I use a light with the same color as the object I'm looking at, that object will appear brighter because it is reflecting more light. Again, we mentioned that the color you see in an object is the light that's reflected and left over from what is absorbed. So if we add more light of the same color of the object, then we get more photons reflected off the object and thus a brighter color. And then the other way to look at this is opposite colors darken. So we have a color wheel here in the top right. If I pick a color like blue as the color of interest here on my object, then directly opposite on the color wheel is orange. Or similarly, green is complemented by red opposite on the color wheel, and yellow by purple, and so forth. And same for the halftones if you keep going around there. So when we say opposite color, we mean the color that is directly opposite on a color wheel. Light with the opposite color then tends to make the object go dark, because of course the object again is absorbing those colors and reflecting the color that is opposite on the color wheel. So how does this work? Well, what if we were looking at this target? In a monochrome world, we're using a monochrome camera and white light. Everything looks equal on this target, and if we were doing gauging or other things, our dynamic range would be high and our spatial resolution would be high for making decisions. But this is the real target with the color camera and white light, and you can see that I've purposely colored the words here and the target. And in certain machine vision applications, it might be necessary to highlight or darken some of these features in order to perform other inspections. So if you look at the rules we just applied, then if I look at that same target with a monochrome camera, but apply red, green, and blue light above each as you see, then you see the corresponding target either brightens or darkens. So the colors here for smart vision lights are red, green, and blue. And if you look in the first example with the red light, you will see that the red text gets brighter, starts matching the white background in fact, and that the green and blue get darker. And similar for the green and blue as you go down the examples here. The opposite is true if we want to suppress or enhance colors. So what if we were doing machine vision? You saw in this previous example that I used red light, and the smart out of smart vision, it actually faded into the background. Even though it's enhanced and brightened, the background is bright or white in this case, and you lose contrast. And maybe I wanted to see the word smart and separate it from vision and lights. The way to do that then is use complementary colors to suppress and enhance the contrast. So in the first example, we've shown it with blue and green light, and you'll notice the red then darkens, steps out the contrast from the background, and the green and blue words actually fade, get a little bit lighter and fade into the background. And again, same if we did red and blue and red and green, you can see that the word that is darkened and separated from the other words moves in each of these cases. The real world effect is a little better, I will say, as we put this into presentation. This effect got minimized by kind of the dynamic range and things going on in presentation, but you'll see some other examples coming up in the real world with stronger effects than this. So let's look at a more real world example. What if we wanted to identify and isolate only the blue M&Ms? Then we're going to remember our rule that light with the same color makes a given object appear bright, and light with an opposite color makes it go dark. So we want to make the blue ones stand out from all the other colors in this case. So I'm going to turn all the other colors dark and make the blue ones stand out. And you can see the white light image on the left where we see full color imaging, all the colors. And even though there's more color information there, there's also visual noise. It's harder for the machine vision to use a color tool and go pick out blue from the red, orange, and green M&Ms and yellow M&Ms. You can use color tools and do it, but this is kind of visual noise. It's much simpler to simply use blue light with a monochrome camera, and you'll notice that the blue M&Ms got brighter, stand out from all the others, and that all the others being primary colors got very dark with the blue light. And this makes it very easy then. You'll see the last image on the right, we simply set a threshold, and you'll see the machine vision software is able to easily pick all those other M&Ms and eliminate them. They're highlighted in red, showing that the tool has found them and eliminated them, and leave only the blue ones there for further inspection and whatever we would be doing in this process. We then can also look at using these same techniques for color suppression. The same rule applies with the color wheel at the top, but now we're going to look at this is a real image from a Gerber baby food jar. And the item of interest in this is the machine vision system needs to see the date and manufacturing codes on the top, but the label is actually very shiny, and there's a lot of blue print. And if we go back to basic good imaging and signal noise, we want the signal from the red print to be very strong and have contrast away from the bright background, but yet we want to decrease the contrast to all the other visual noise, which is just noise for our machine vision tools to pick out. So we want to remove the blue art and other print, and we want to read the red code and make it stand out from the bright background. And the answer to this is we will light with a blue light. Then when we use a monochrome camera, the blue print, which matches the blue light, is greatly minimized. And you can see that in the monochrome image on the right there. You can still see the print, especially against a shiny, perfectly reflective top there, but it's so minimized that it's very easy then for the machine vision system to go in and see the red print, which is now dark against the shiny background, and go pick it off, and easily then do OCR and read the things it needs to know about the date code and the other manufacturing code there. And you'll see color suppression was also used in two ways here. Number one, the color suppression, we suppressed the blue print into the bright background, and then we also used suppression, which is a way to darken, to make the red print darker to stand out from there. So, we get both effects and use the fact that the red and the blue print were kind of separated on the color wheel, and that we could find a way to eliminate one and increase the contrast in the other. And then as we look at the bottom example on the right, we have a white bottle with red print, and same thing, we want to see the date code. But now the date code is done in blue. We have the opposite problem. And what color would you use to suppress the red print and enhance the blue? Well, looking at the color wheel, you can see it's almost just the opposite. We're going to use a red light in this case because we're dealing largely with primary colors, and red is enough. We could have also used our orange light, which, if you still want to see the print some, which was suppressed it but not completely, and made the blue even darker. So some of these things you don't have to be very specific. It's easier to get a primary red light than an orange light. And when we have red and blue print, you may have to make choices between whether you choose red to perfectly eliminate the red print and get good contrast to blue, or whether you choose a mixed color like orange to get the darkest contrast out of the blue but may still leave some of the red print. Color enhancement also works the other way around. In this example, we have red text with a white light and a monochrome image on the bottom of a can. And if we just image it with white light and a monochrome camera, the background is reflective, and though there's pretty good contrast on the red print, you can see it's hard to see, and especially in the smaller manufacturing code there, that the character strokes are a little bit thin, and with the bright background, you don't get as much contrast as you would like. We want to enhance this red text, and we want to minimize the background effects, and we're going to then use light with an opposite color in the color wheel and make this stand out. So the white light on the bright background gives bright red text, but also bright background, no contrast. If we then use blue light, which you see in the example on the right, then you have the red text with the complementary opposite blue light, which is then darkening that red text. And you see the text gets much darker, the character strokes come out with much better contrast, and of course this is much easier for your machine vision system to pick out in the real world. And for doing this, again, when you're looking at these, you want to use color to get these kind of results. But did I really have to use white light and a color camera? In these kind of examples, the answer is no. The color data may have made an operator feel good about what he was seeing, but the color really offered nothing if we had a 24-bit full color image, just more data for the system to process. And even if you go to monochrome, just using white light, which is natural, didn't produce the best result. And by simply buying a blue light instead of a white light, you can get a much better result at no additional cost and with less data and less complexity than doing a true color application to separate the red print off the background. Lastly, I want to make a note about filters here. We have largely talked about using colored light, but in some cases, you may have combination things. You may be forced to use a white light. You may be using multiple cameras on an application and need to see different things with different cameras. You may also have light pollution, going back to signal and noise. You may need to be using color effects like we're talking about here, but you may have ambient light coming from overhead fluorescent lights on the factory floor. You might have sunlight coming in from a window. So always remember there are filters to either give these effects or enhance effects. So you see on the top right, there's a transmission chart for a bandpass filter, which is only blue. So if we were doing an application where we needed to use blue light and get good contrast on red text in the previous examples, then you started getting the effect you wanted, but had overhead fluorescent lights, or worse yet, your situation is dynamically changing because at 3 o'clock in the afternoon, there's a lot of sunlight hitting it and diffusing your blue light and diluting the effect. Then using a bandpass filter is a good way to go in conjunction with the blue light and get the best signal to noise. So you're going to pass the blue light with near 100% transmission through the filter, but you're going to block the majority of the wide spectrum light coming from the overhead lights or sunlight. And you can also use these kind of filters. In some cases, as I alluded to, you might need white light because you have other cameras, you have a color camera and a monochrome application or other things. So you might be using a white light, and you could simply use this blue bandpass filter also to get blue on the specific monochrome camera to still get the color effects we're talking about, but still use white light needed for other parts of the application. It is notable, though, that it is preferable to use the colored light rather than white light with a filter if there are no other factors for you. Because again, good imaging is a factor of the signal to noise. So if all the signal are blue photons filling the well in the pixel, then that comes from blue light and either no filters or ones with a very high transmission rate in the area, and you get the best signal to noise. If you use white light, then for every watt of power you put in that white light, you're getting a full spectrum, and then you use the filter to filter out of that. You're using only a narrow slice of that full spectrum, and your power is reduced. So there's wasted signal to noise by using a white light and a blue filter. Again, this is okay if there are other factors that lead you to mix these filters and use a white light. But if given no other choices or no other factors rather in the application, then it is far better if you need color effects to start with the right color light and use filters only where needed for blocking or further contrast enhancement. You can also see on the bottom right, filters come in a number of colors, as we show on kind of the general filter diagram in the middle. And you can get those colors and band passes on the top right. But on the lower right, you can also see those cutoffs, short pass and long pass filters that cut at a frequency and pass everything else. So, in cases where we're talking about blue-green effects and blocking red or so forth, you might actually use a high pass filter or a short pass filter and leave those colors in and block the red with a full filter. So knowing how to use filters and looking at these, we certainly have expertise. You can talk to our application engineers and get additional help with filters in conjunction with our lights and helping you with your general imaging. But knowing a little bit about filters can help you increase your application and get a better result, even if you're using colored light or mixing with white light and needing to use these color effects we're talking about. So at the end of the day, know the wavelengths of the light you're using, know the filters available, and mix and match these using the good color principles we're talking about to get a good result. Lastly, as we start to wrap this up for today, I want to remind everyone that LED lighting comes in many colors. You can see sample lights on the top left here. On the right are typical wavelengths that Smart Vision Lights offers in our standard lights. This is not specific to any one light, but these are general. There are actually many more in between. And you can see the variety of products on the bottom left there. All these products are available in some color combinations, and those color combinations might include UV or SWIR or near infrared. So even to use the effects we're talking about, you don't necessarily have to be dealing with visible color. But when you look at the far bottom right, then you'll notice these are showing mixed wavelengths that are available to SDL from other manufacturers, and this is just a sampling. There's many more. So we encourage you always, if you need something in between the standard offerings, to come talk to us, because often on a special order basis or a custom basis, if you're talking about us building custom lighting for you, then we have many more choices. We have to break these down to standards for the general market and keep everyone in, to keep the volumes high in certain buckets like anyone would do with standard product management. But we actually do have many, many choices in LEDs today throughout spectrums, from the ultraviolet all the way down into near infrared as shown here, but actually including SWIR as we go further into the 21st century, and there's more and more development and interest in non-visible imaging. So there's always a good choice of LEDs, and we can offer you things outside of the standard if you're not seeing what you need for an application. And again, talk to our application engineers and come to us for expertise if you do need help with this or think that you're not getting the result and need something in between standard color offerings. I also want to mention that in addition to fixed color lighting, SVL offers multiple color lightings. This is an example of what we call a DualAxis diffuse light, DADL. It's a specialized light. We talked about it for filling the hole in the sky in previous presentations, but it actually happens to be red, green, blue color mixing here so that you can turn on the primary channels, and the three pictures at the top show 100% of the three primary red, green, and blue channels. But at the same time, you can mix them in any ratio using the knobs and create basically any color. So I just mentioned that we have many color choices available on special orders. We can do in between colors for you. But the other thing you can do is buy multicolored mixable lighting like this and mix to get any color you need and exactly tune an application. It's notable that this is an area of interest. Besides red, green, blue, like shown here, there's lights coming with red, green, blue, and a white channel. So you can have white as a baseline, but you can also mix red, green, and blue to get any color or offset that color with the white to get fainter colors. And Smart Vision Lights has many RGBW products coming in the following year, which will help you with tunable color selection and better fit your application. That's going to wrap up the presentation for today. I want to remind you, as always, Smart Vision Lights is your partner for imaging. We'll help you to win business and get your image right. We want to be your go-to for the how-to. Please do come to us if you have questions or need application support. We are happy to provide that and show you what it takes to do a certain application. I want to thank everyone for participating today and encourage you to watch future segments of these kinds of presentations where we're doing monthly trainings now. And every month you will see these trainings and probably other material that we're putting out there. Also watch our social media pages. Thank you very much for attending today.